Okay, so as we continue 11.2, a couple things I want to talk about here. This table is on page 502. Now this is the table of indefinite integrals, and notice that it has antiderivatives in the brackets. Okay, we've got the integral notation. Okay, notice the elongated s, right, and the integrand, the d of dx. It's indefinite because what it gives us are formulas, right, not actual values. It's not definite, it's indefinite. And really, these are the same as the antiderivative table that we took a look at in chapter 9. So the first one, for example, we have x to the power of n, right? Just a reminder, what you do is you add 1 to the exponent of x, and then you divide the coefficient, or this whole term, really, by that same number, n plus 1 and n plus 1. See that? And that's the rule. That's how we find the antiderivative of just a variable with an exponent. Now, if the variable has an exponent of -1, that's a special case. And what we do there, instead of turning it into a constant, which doesn't make sense, right? You have -1, you add 1, that's 0, then you divide by 0. That doesn't work. So that's why this is a special case. And the antiderivative, or the integral of 1 over x, is the natural logarithm of x, or absolute value of x. Okay? Plus c. Of course, all these are plus c at the end, right? So this is in your textbook, but I'm just going to take a minute to highlight just a couple things. So the antiderivative of sine is negative cos. Okay, so the integral of sine x dx is negative cos x plus c. The integral of cos x is sine x, and so on. The rest of these right here, if you encounter these, you'll be able to kind of refer back to this chart, and you'll say, hey, I have 1 over x squared plus 1, and I'm finding the integral. You would have no idea that the indefinite integral of this right here would be tan to the -1x. You would have no idea, but it's in the chart. So if you run into something like that, and you're thinking, how do I tackle that? Check the chart first, because you may have some indication. Okay, so this one's a bit different. I will highlight this one though. Okay, up here, the very first one, this is x to the power of some number, constant. This is some constant to the power of x, right? So that's an exponential, right? Function, exponential. So it'll be like 2 to the power of x or something. Now, as long as this a value is not 1, then this is the integral right here. It's that 2 to the power of x over ln of 2. And you should remember that, maybe, from our antiderivatives when we studied chapter 9. Okay, so this chart should be very helpful for you. I'll get rid of my markings and my mess here. But yeah, this chart will be something that you'll be able to refer back to when you're doing some of these. Any questions on that so far? Yep. This one, sin x? Okay. Why is this negative cos x? Because remember, when we take the derivative of cos, it's negative sine. So if we have negative sine and we take the derivative of negative sine, we get negative times negative sine, which is positive sine. So yeah, if you're thinking about derivatives, it's really the antiderivative is opposite, right? So it's opposite sign as well. Okay, so yeah. Any other questions? All right, so really quickly, I'll just move on to this next part here. This is basically, we're going to do this real quick. I mentioned this in the last lesson, that if you have an integral, and you have inside here, okay, what we're integrating, if you have a constant in front of a function of x, you can move that constant out. That can come outside of the integral sign and just stay there as a constant, and then you can just kind of be concerned with this part. And that constant just stays out there. Really, it's the same as the derivative, really. Like if we have 2x to the 5, right? If we take the derivative of this, then being that this is a constant and this is a function of x, you can do this, 2 times the derivative of x to the 5. You could. That's basically what we can do, and that's what we actually do but we don't actually show this step, right? Because this is like 2 times, and taking the derivative, so that's 4x to the fourth, right? Sorry, 5x to the fourth. Getting my integrals and antiderivatives. So 5x to the fourth, right? So it's the same as when this number comes down, it's the same as multiplying by this. But that's the derivative, and here's the constant, so that's why it equals 10x to the fourth. So that's the same rule for integration. This one, a no-brainer. This looks super confusing, but all it means is that if you have like a polynomial with different functions of x, like x squared and then 2x, you just take the integral of each term and you add them together. It's really, I mean, I hesitate even to mention this because it's almost second nature. And you've been doing this already with these assignments that I gave you before, right? And even this one right here, see? You take the integral of this and you add it to the integral of this. That's exactly what we did. See that? So you're doing this intuitively already. Okay, so here's an example where we're looking for the indefinite integral of this function right here. Okay, so the integral of x minus 5 over the 4th root of x dx. And so what we want to do is find the antiderivative of this function. Now this looks a little confusing with the 4th root of x, but what we can do is we can, basically, we can take this and rewrite it. And that's what I'm going to do. What if we did this? The numerator, okay, and if we change that 4th root of x to the 1/4, okay? If we did that, and then we said, you know what else we're going to do, is I'm going to actually change this to x minus 5 times x to the negative 1/4, because I'm going to bring that up from the denominator. And likewise, if we kind of keep going on that path, then I can distribute this to each term. And when I have the same base, I simply add the exponents. So that's going to be x to the, what's that, 3/4. 1 minus 1/4. 1 minus 1/4. That's 3/4, right? No. You don't do that. Because when you don't do x squared and then this, because when you multiply with same bases, the only thing you do is add the exponents. That's what we've done. That's what you've done your whole life. Like x squared times x cubed. It's not x times x and then 2 plus 3. It's not that, right? So yeah, don't psych yourself out. No, we just add the exponents, and that's what does it. And then, so this is times 5. It's minus 5 x to the negative 1/4. Okay, so does that look right? So that's what this is. So we could really rewrite this as the integral of this polynomial, x to the 3/4 minus x to the negative 1/4 dx. And then we can use our rules and simply take the antiderivative of each term, right? This term, and we'll subtract them. So what's the antiderivative of x to the 3/4? Well, we go back to our rules, which are right here. And basically we have this, right? Right? So what are we going to do? We are going to add 1 to this, right? So 3/4 plus 1 is going to be 7/4. And then what do we do with the new exponent here? We what? Divide by that exponent, right? Or multiply by 4/7. Is that agreed? And then we're going to subtract. Now let's do the same thing here. What if we add 1 to negative 1/4? We get x to the 3/4. And then if I divide by that, I'm going to basically times by 4/3. Okay, is that looking right? We good with that? So to simplify that then, 4/7, x to the 7/4, minus 20/3, x to the 3/4. Plus c. Oh, wait, what? No, this negative went away when we added 1. It came into the positive. See, it made it like negative 1/4 plus 1. Made it positive. Okay? So let's just check to see if we did that right. Nope, not that one. This one. Okay, so here's our answer key. And which question was this now? E? All right, so does this look like what we have? Hey, I think so. So that's the answer right there. And they did it the same way. They rewrote that, this function right here, as sort of a subtraction of terms instead of one rational. All right. Circle that, and we'll be done. Okay, so that's your example there. Again, just some extra integration rules. Again, we're going to talk about, what is it? The substitution rule, that's as a rule for, or as a method of integration. We're going to talk about that next lesson. But here's just sort of a continuation of some basic integration stuff with some of these basic rules right here using this table of indefinite